Hello, calculus students. We are currently in chapter 3 and we're going through the process of learning all the derivatives and we are right here, section 3.8. We're going to take a look at the derivative of inverse trigonometric functions. So let me go back into our notes and we'll begin. Okay, just to kind of review a couple of things that we've talked about before, the Pythagorean identity for trig is sine squared plus cosine squared equals 1. If I were to divide, there's actually two more of these Pythagorean identities. If I were to divide all of these by sine squared to everything, then this would be the second Pythagorean identity, 1 plus, let's see, cosine over sine, that's cotangent squared x, and 1 over sine, that's going to be cosecant squared. That's one of them. Now, if I were to divide everything by cosine squared to everything, I'm going to end up with a, let's see, sine over cosine is a tangent, so it would be tangent squared plus a 1 equals, and 1 over cosine is secant squared. So there's actually three Pythagorean identities that we're going to relate to. There's the first one, second one, and the third one. Now, the reason why I'm sharing this with you is because we're going to later on use these as our proofs. So we're going to first talk about sine, the inverse of sine, the inverse of tangent, and the inverse of secant. So I think what I'll do is, since we have time, I'm going to show you the proof of the inverse of sine. Now, I'm going to be very straightforward. These derivatives are not going to be very clean looking at the end, but here's the proof of the inverse. Actually, here's the result. I'm going to show you the end and how we get there. So this is the derivative of inverse sine. It is 1 over the square root of 1 minus u squared du dx. That u is just for doity, the chain rule. So if you have something other than an x inside the inverse of sine, then you have to apply the chain rule. That's why the du dx is there, the derivative of the inside. Okay, so if you're curious, why is the inverse of sine this big, messy 1 over square root and so forth? Well, the proof, I'm going to first rewrite this as sine y equals x. I have the inverse of x. Well, I'm going to solve for x, so I have to I'm going to sine both sides, and I get sine y equal to x. Now I can take the derivative of both sides. This is written implicitly. So if we take the derivative, cosine y, the derivative of the inside is a 1, but with respect to x, it has to be dy dx, equals a 1. X becomes 1. I'm going to solve for dy dx. That's 1 over cosine y. Now, I do not want my derivative with respect to x have a y in it, so I have to go back and substitute. Well, cosine y, what is cosine y? Well, you know what I could do is use Pythagorean identity. Sine y squared plus cosine squared y equal to 1. If I solve for cosine y, I'm going to have to subtract sine squared y and then take the square root. So let me go back and replace 1 over square root 1 minus sine squared y. Well, what is sine y? Sine y equals x. So therefore, it's 1 over the square root 1 minus x squared. So that is the derivative of inverse sine. So down here, like I said, you have a u. So this is the general form for the derivative of inverse sine, that u could be something other than an x. So for example, the first derivative right here, the derivative of inverse sine of 3x squared, it is going to be the chain rule here. So I'm going to write down y prime. It will be, I'm going to follow the model up here. It's going to be 1 over, it's going to be a square root, 1 minus, what's my u? The u is going to be the inside. Here's the inside. So it's going to be 3x squared. and I have to square that, and then I got to take the derivative of the inside, and thus that's going to be 6x. So then I just want you to simplify a little bit here. I'm going to put 6x on top, take the square root, 1 minus 3x squared, and the whole thing squared would be 9x to the 4th. Now I'm happy with that. You may be looking at answers elsewhere and they would rationalize it, or they would factor out an x to the 4th, 9x to the 4th, but I'm happy as is. So this is something where you're just going to have to remember the derivative of inverse sine. It's 1 over the square root of 1 minus u squared and then du dx. Okay, for the next one, inverse of tangents. I'll just go ahead and show you what the derivative is going to be. Again, these derivatives are not going to be nice and neat, not clean. It's going to be a little bit messy. It's going to be a fraction, 1 over u squared plus 1, and then, of course, du dx, meaning the chain rule. So you're probably thinking, well, why is that? Well, the same thing. I'm going to go ahead and solve for my x here. So I'm going to take the inverse of tangent. I'm going to multiply everything by tangent to get tangent y equals x. I'm going to use implicit differentiation, what we just learned prior to, and it's going to be the derivative of tangent is secant squared y, and then the derivative of the inside is a 1 dy dx. I'll write y prime this time, equal to 1. You're going to solve for y prime, so it's 1 over secant squared y. Well, what is secant y, or what is secant squared y? Well, if you go back to our opening, we talked about Pythagorean identity, and it looks like secant squared is going to be tangent squared plus 1. So we can use that identity to write it out as 1 over tangent squared, that's a squared y, plus 1. But again, we don't want our derivative with respect to x to have a y in it. So is there a substitution we can be made with tangent y? And we can go back, and tangent y is an x. So therefore, our derivative is 1 over x squared plus 1. Okay, so for example, I'm going to take a look at this example right here. The derivative of a particle moves along the x-axis so that its position at any time t of x of t equals the inverse of tangent of the radical of t, square root of t. What is the velocity of the particle at 16? So I'm just going to go ahead and rewrite our function as t to the 1/2. So I'm going to apply the derivative. So the derivative of this function will be 1 over something squared plus 1, and then the derivative of the inside. And that inside is t to the 1/2. This is the inside. And the derivative of that is 1/2 t to the negative 1/2. And I'd probably clean this up here a little bit. Let's see here. I'll start out with this term right here. T to the 1/2 raised to the second is just a t, so it's going to be t plus 1. I'll put that in parentheses. I have a 1 right here. I'm going to rewrite this 1/2 as 1/2, and t is on the bottom. It's a negative exponent, so I drop it to the bottom. So I'll just take the time to make one big fraction. I'll put t, or 2t, 1/2 t plus 1. Now, I didn't answer the question yet. It says, what is the velocity when t is 16? So I'll substitute 16 into our derivative. 1 over 2 times, this is really the square root of 16, and 16 plus 1. Let's see, I'm going to get an 8 and a 17. And if we multiply that out, that's going to be what's here, 80 and then 50, 136. Okay, so that is the derivative of the inverse tangent, an example of that. And I'm going to go ahead and conclude this video and to bring up the inverse of secant.